Welcome back, geometry students, as we continue to talk about triangles. In this lesson, we're going to focus on categories of triangles. We have two different ways of classifying triangles. The first way is by their angles. One type of triangle is the acute triangle, and that's any triangle that has three acute angles as its three angles. This is an acute triangle. Notice that all three of its interior angles are acute. Hey, can you even, first of all, a triangle, all three of the angles have to add up to 180 degrees inside a triangle. Can you make 180 degrees by adding together three acute angles? Yes, very easily. Is it possible to make 180 degrees with an obtuse angle? The answer to that is yes. An obtuse triangle is any triangle that has one obtuse angle. Hey, an obtuse angle is greater than 90. Could you make a triangle that has two obtuse angles? The answer to that is no. Because if you have two angles that are greater than 90 degrees added together, you're already at over 180, and you wouldn't be able to make that triangle. So only one obtuse angle is possible, and that's what makes an obtuse triangle. The other two angles will be acute. And then lastly, a right triangle has one right angle. Now think about this. Could you have a triangle that has two right angles? Well, two right angles would equal 180, but then there wouldn't be any degrees left over for the third angle. So no, there can't be a triangle that has two 90-degree angles. So you can either have a triangle that has all acute angles, one obtuse angle, or one right angle. And these are the three types of triangles according to this classification system: acute, obtuse, and right. We have another term that we could use to describe some triangles. A special kind of acute triangle is an equiangular triangle, also sometimes called a regular triangle, which has three congruent angles and congruent sides. The other definition of a regular triangle is it's a triangle that has enough fiber in its diet. All right, moving on to the next part of this, we're going to classify triangles another way in addition to calling them acute, obtuse, and right based on their interior angles. We could call a triangle equilateral if it has three sides that are the same length. Again, this is a regular triangle. An equilateral triangle is automatically equiangular as well. Now, hey, how is this a different classification system than the classification system above? Up above, we were classifying by angle, okay? That's why equiangular angle was up here. Equilateral, lateral means side, equal sides. An equilateral triangle is an equiangular triangle. They're the same thing. It's just this is categorizing it by sides. What other side configurations can we have on a triangle? Well, if we have two sides that are congruent and one side that is not, we call that kind of triangle an isosceles triangle. Now, notice the definition: at least two congruent sides. That means that all three sides could be congruent. Does that mean that an equilateral triangle is a type of isosceles triangle? The answer to that is yes, according to the definition of isosceles triangle. I can already picture the Venn diagram of isosceles triangles, and an equilateral triangle is inside that Venn diagram. And then lastly, a scalene triangle is a triangle that does not have any congruent sides. All of the sides are different lengths. This scalene triangle is an obtuse triangle, but you could also have a scalene triangle that's an acute triangle as well. You could have a scalene triangle that's a right triangle as long as all three side lengths are different. We've run into lots of those right scalenes, and we're going to see a acute scalene later on in this lesson. All right, then the last thing, how do you find the area of a triangle? This is a formula you should be well familiar with. The area of a triangle is given by the formula where B is the base of the triangle, the length of the triangle's base, and H is the height. Now remember, the height of a triangle has to be perpendicular to the base, or at least perpendicular to the line that contains the base. And this is the equation. Now, if you're interested, I have here a proof that the area of a triangle is 1/2 the base times the height. First of all, let me show you an example triangle. I just want you to pay attention to this, okay? It's a little tough to see it. Let me see if I can zoom in just a little bit here. So notice here that I have sides EA, CD, of EC here, this little side, and then CD, DB, BF here, and then FA is this little side over here. So I have a rectangle, AE, ED, DB, and BA. These four sides bound a rectangle, and then I've got all of these triangles drawn on the inside. I have triangle BCD, CFB, AFC, and CAE. Now, what is this triangle showing? Well, you see that I have a rectangle, ABDE, and inside I have triangle ABC. Notice scalene triangle, A here, B over here, and C up here. That's the main triangle that I'm trying to find the area of, okay? But also notice that I have little triangles inside. AFC is this little one right here, and CEA have the same base and height. So if I choose, the way that I would do this is for these two triangles, I would choose AF as the base of one and CE as the base of the other, but those are the same lengths because this is a perpendicular line, so it's going to move up along parallel to this line, and it's going to cut the same lengths off of the triangle. So the bases are the same length, the heights are the same height, so therefore the areas, if the base and the height are the same, the areas have to be the same. The area of triangle 1 and triangle 2 are the same. And the same is true for triangles 3 and 4. Bases, same length. Height is exactly the same. So the base times the height times 1/2 is going to give us the same area. So A1 and A2 are equal areas. A3 and A4 are equal areas. Now we're going to see a proof that's like a visual proof. This isn't like a 2-column proof like we're going to be working with later, but it's a really cool visual proof of this concept. So the area of angle ABDE of the whole rectangle has to be equal to the sum of all of these triangles inside. Does that make sense? Triangle 1, triangle 2, triangle 3, triangle 4. I add all four areas together. I get the area of the rectangle. Okay, next. The area of a rectangle is base times height. So the base of the rectangle, which is this whole AB here, and the height is BD. Now let's just think about base times height. The base AB is also the base of my interior big triangle ABC. You see that? That's the base of that triangle. We'll just keep that in mind. All right, now, we said that A2 is equal to A1, and A3 is equal to A4, right? These interior areas are the same. So I'm going to replace all my A2s with A1s because they're equal. I'm going to replace my A4 with A3. Base times height equals 2 times area 1 plus 2 times area 3. And then I'm just going to factor out that 2. Base times height equals 2 times area 1 plus area 3. Because area 1 and area 2 are equal, so I don't have to include area 2. Area 3 and area 4 are equal. Now, moving on to the next part. What if I divide both sides by 1/2? I get 1/2 base times height equals area 1 plus area 3. And wait a second, what is area 1 plus area 3 up here? Why, area 1 plus area 3 is the area of triangle ABC. So there's a visual proof that shows you in a creative way why the area of this triangle is 1/2 the base times the height. And that kind of proof works for any kind of triangle. You'll always find that the area of a triangle is 1/2 the base times the height.